Hi, welcome to our video on internal or thermal energy. So far we've talked about three different types of energy. We've talked about kinetic energy, the energy objects have because they're moving. We've talked about gravitational potential energy, the energy that objects have because they're up above some massive object. And we've talked about spring or elastic potential energy, the energy that is stored in objects when they are either stretched or compressed. All three of those types of energy can be kind of lumped together under the category of mechanical energy. The reason they can be lumped together is it's very easy to change one of those types of energy into another. For instance, if you throw something up in the air, initially it has kinetic energy, but as it rises, it loses that kinetic energy, and that kinetic energy actually gets turned into gravitational potential energy. On the way back down, the reverse happens. You could also have an object that's moving with kinetic energy along some surface, and then it strikes a spring, let's say, and it starts to compress the spring. The object will lose kinetic energy and it will gain elastic potential energy, and then again vice versa as the object after the object stops and once the spring starts to push back on it and send it back out. The type of energy we're going to be talking about today, internal energy, is not a type of mechanical energy because it's not easy to convert internal energy back into the other types of energy. Once energy has been transferred into internal energy, it's pretty much not coming out, at least for our purposes, it's staying there. The definition of internal or thermal energy, you can really say either, but I'm probably going to favor internal, is any type of energy that is stored as heat in an object. Okay, any type of energy that's stored as heat in an object. Basically, if an object has more internal energy, that means it has a higher temperature, which means on a molecular level or a microscopic level, the molecules in it, molecules, not molecular, the molecules are simply moving faster. That is how we perceive heat. When we perceive that something is hot, when we perceive something with a high temperature, that's just us kind of reading how fast the molecules are moving or vibrating within that object. Okay? So internal energy, energy stored as heat, I can show you a conversion from kinetic to internal energy right now by just taking my hands and rubbing them together. Everyone knows that that makes your hands warmer. What's happening is the kinetic energy of your hands is being turned into internal energy, so your hands heat up. That's what you do in the winter. Now, why exactly does that happen? How does an object gain internal energy? Well, it has to do with the hands touching and rubbing past each other. There's some friction there. So friction, or just contact in general, causes a temperature change. And we're not really concerned with the temperature change, but you could measure the effect of internal energy by having something like having the force of friction act on something over a long period of time and then measuring the temperature both before and after that happens. You should see at least some sort of change. It's probably going to be very small for most objects, but you should see some type of change. There's actually a lot of ways that objects can gain internal energy, but we're going to focus on them gaining internal energy through friction. As far as the derivation goes, you'll notice on the reference tables that there's not really an equation for internal energy. There is a symbol for it, and I'll write it down. The symbol is Q, capital Q, which you should be used to from chemistry. We're using the equation Q equals mc delta T to talk about how much energy is put into something to cause a temperature change. You also talked about the amount of energy Q needed to cause something to melt or to vaporize. So you're a little bit familiar with Q as a symbol for energy. I said that we're going to focus on how objects gain internal energy through friction. Let me give you an example. Let's say you have an object. And we'll just do a really simple case. This object is, let's say, just no one is pushing it, but it's just sliding on some surface. Okay, so there are three forces on this object. Normal force upwards, force of gravity downwards, and then the force of friction. Let's say the object is sliding to the right. Force of friction would act back to the left. Now, just like all the other types of work, when we define them, we first started looking at how different forces were doing work, or how much work was done by certain forces. We're going to do the same thing here. We're going to figure out the work done by the force of friction. So I'm going to write down WF equals the force of friction. So work done by force of friction equals the force times the displacement times the cosine of theta. So I know just by looking at this that the displacement of the object is to the right, the force of friction is to the left. That means that the theta I put in for the cosine theta part would be 180 degrees. And as we know, the cosine of 180 degrees is -1. So right away, we're already getting a negative sign in for the force of friction. I know that if this object is moving, that we can use the equation mu Fn for force of friction. Okay? When we're dealing with kinetic friction, then we can say that the force of kinetic friction is equal to, let's get the negative out there, mu k for the static or for the kinetic coefficient of friction times the normal force times the displacement. We can even go a step farther and figure out what the normal force is if we do a net force equation. F net y equals Fn minus Fg equals may. Running out of room there a little bit. Let's say that this object, well actually, may. This object is very clearly not accelerating in the y direction, so the acceleration is 0. Therefore, Fn equals mg. And if I'm asked to find the work done by the force of friction, I can give the equation mu k times m times g times d. Okay, I can figure out how much work is done by the force of friction. Now, notice that this is negative. All the rest of these are positive terms. Okay, so the work done by friction is negative. What does that mean? Well, remember what we mean by work being done. Energy is either flowing into or out of a system. In this case, the work done by friction is negative because mechanical energy decreases. So you might be tempted to ask, well, where is that mechanical energy going? If I go back to the example of rubbing my hands together, okay, where is that energy going? The kinetic energy, if I didn't keep rubbing my hands together, my hands would eventually stop if I wasn't actively trying to push my hands past one another. But what type of energy is increasing? It's got to be internal energy because you realize your hands are getting warm. So the work done by friction is going to be negative in any case where friction is doing work because it's taking mechanical energy away. It's decreasing, in this case, the kinetic energy. But that energy's got to go somewhere. We know that the internal energy must be increasing. If this object is sliding over a floor or some surface, the surface is probably getting a little bit warm. So the internal energy increases. Well, the internal energy is Q. And before this, we could assume, at least at this level, that the internal energy was 0. If something is 0 and then it increases, it must be positive. So Q itself must be positive. So the work done by friction is negative, but Q, the internal energy, is positive. How do I get around this? The relationship between internal energy Q and the work done by friction, WF, is as follows. Q equals negative WF. But I want you to think about this for a second, okay? So this is not in the reference tables. Internal energy equals negative WF. Internal energy is the negative of the work done by friction. Let's go back to our work done by friction equation. That itself was already negative. So if I were to plug this in, I would get 2 negatives out front and then all these terms. You know that 2 negatives, a double negative, will just turn into a positive. So one way to calculate the internal energy of a system is given by this equation for an object that's sliding over the ground. This is not the only case that you will see with internal energy, but it's one that comes up a few times. Again, this is not in the reference tables. This is something that you must derive. Okay? So please understand the difference between the work done by friction and internal energy. They are the negatives of each other. Okay? The work done by friction is always going to be negative. The internal energy is always going to be positive. One way to calculate the internal energy is by using this method if you have something sliding over a surface. Again, this is not always going to work. There are other cases where you simply calculate Q based on how much mechanical energy was lost. That's another way to calculate Q, but that's usually a little bit easier. I wanted to show you the tougher version here. Let's get into our more extended example. A 30-kilogram wooden crate starting from rest is attached to a rope and dragged along a wooden floor for a distance of 8 meters. First thing, let's draw a free body diagram for the box, or the crate. So there's our dot, label it crate, X, Y, plus. We've got a force of gravity pointing down, Fg. Let's say the crate's being dragged to the right. It's dragged by a rope, so that's tension. Normal force pointing upward. And the force of friction backwards. After the free body diagram, we immediately write our net force equations. In the x direction, that would be T minus Ff equals max. And in the y direction, the normal force minus the force of gravity equals may. And we don't exactly know what's happening in the x direction, but we could probably give a pretty good guess as to the y direction what's happening. It's probably not accelerating up or down. No acceleration in the y direction. Therefore, the normal force is equal to Fg, which means the normal force is equal to mg, mass times acceleration due to gravity. Here's an old question from the forces unit. How much force is required to just barely get the box to start moving? If we just barely want to get the box to start moving, that means that when we have this equation, T minus Ff equals max, basically no acceleration, which would imply that the tension is equal to the force of friction. If we just want to get it to start moving, that means we're just barely overcoming the force of friction that's active when the box is at rest. That's static friction. And if we're just barely overcoming the force of static friction, that means we're allowed to use this equation. The force of friction is equal to mu Fn. We can't use that for every case of static friction, but if we're just barely overcoming the force of static friction, if we want to know the maximum force of static friction, then it's okay. So I'm going to bring the Ff to the other side. I'm going to write mu s, just so we know. You don't have to write the s, but that's just my reminder that we're dealing with static friction here, times Fn. We already found that Fn is equal to mg, so this is really mu s times m times g. The tension required to just barely get this to start moving is equal to the static coefficient of friction times the mass times the acceleration due to gravity. We have the mass, 30 kilograms. We know acceleration due to gravity on Earth, 9.81 meters per second squared. What's the static coefficient for this situation? We have a wooden crate on a wooden floor. That's one of the coefficients of friction listed on our reference tables. Wood on wood, static, 0.42. Remember, that does not have any units, but the rest of these numbers do. Turns out the tension needed to just barely get this wooden crate to start moving is 123.6 newtons. I'm going to go ahead and box that in. Okay. This force is kept constant once the box starts moving. How much work is done by this force over the 8 meters? So we want to know how much work is done by tension over 8 meters. So work done by tension would be equal to tension times displacement times the cosine of theta. We didn't draw in what direction the displacement's in, but it's pretty obvious if you're pulling it to the right, this object's going to move to the right. So tension and displacement are lined up. That's an angle difference of 0 degrees. They're in the same direction. And as we know, the cosine of 0 is 1. So this just cancels out. The work done by tension is therefore 123.6 newtons times the displacement of 8 meters. The work done by tension over this 8 meters is 988.8 joules. Remember what work is. That means that's how much energy is transferred into the system of the box. Once the box is moving, what is the new force of friction on the box? That doesn't say new, but it's kind of implying there must be something new. Previously, we said the force of friction was just barely equal to the tension. That was when it wasn't quite moving yet. Well, now it's moving. What's changed? The mass hasn't changed. The acceleration due to gravity hasn't changed. The thing that's changed is the coefficient of friction. Remember that the coefficient of friction decreases once an object starts moving. The static coefficient of friction is always higher than the kinetic coefficient of friction. So we're going to need to use the kinetic coefficient of friction. And in that case, we can definitely use this equation. This equation always works if we're trying to find the kinetic coefficient of friction. The kinetic coefficient of friction for wood on wood is 0.30 times 30 kilograms times 9.81 meters per second squared. The new force of friction is 88.29 newtons. Notice that that's much less than the tension that was required to get the box to start moving. So you can kind of think about it. If you have a tension that's great, that is still the same as what it was, and the force of friction is now less, I predict this box will start to accelerate now. Once you get it to start moving, it'll stay still until your tension is greater than this, and then it will start to accelerate and start moving. So 88.29 is the new force of friction. First question on the back, how much work is done by the force of friction over the course of the 8 meters? Well, the force of friction is back to the left, the displacement's to the right. If we're trying to find the force of friction, that's going to be FF times D times cosine of theta. FF is in that direction, the displacement is in this direction. Those are opposite each other, 180 degrees apart. Cosine of 180 degrees is -1, just like we expected from before for the work done by the force of friction. So this is going to turn out to be negative 88.29 newtons times 8 meters. The work done by friction is negative 706.32 joules. That's how much work is done. Now, it doesn't ask it. I probably should have written this in. What does that mean the internal energy that's been generated so far is? How much internal energy was generated? Well, we can figure that out very easily by doing Q equals negative work done by friction. Since the work done by friction is negative anyways, the internal energy is just the negative of the work done by friction. Now, you might be wondering, wait a sec, we just derived that big hole equation for Q and for WF. Why didn't we use those? Well, if you think about it, we kind of did. We just didn't write down all the steps. We kind of did it in 2 different steps. During the last part, we figured out what the force of friction was. Then we simply figured out the work done by friction and Q. I've got 2 different ways to figure out the net work done on the box. Net work means the total amount of work done, including both positive and negative work. One way is to simply add up the different types of work that were done. Work was done by tension, and work was done by friction. The work done by tension was our 988.8 joules. The work done by friction was our negative 706.32 joules. This comes out to a net work of 282.48 joules. In other words, there was a net flow of energy into the box, into the crate. The other way you could possibly find the net work done on the box is to use the net force. Now, granted, we didn't really find the net force for once the box is moving, but that's easy enough to do. The net force is equal to T minus FF equals MAX. We don't even need the MAX part. We know the tension, and we know the force of friction. The net force in the x direction is 123.6 newtons minus 88.29 newtons. The net force in the x direction is therefore 35.31 newtons. And if we know the net force, that means we can find the net amount of work done. The net amount of work done could be found by doing F net x times d. This is the work equation, cosine theta. Since the net force is directed to the right, because tension is bigger than the force of friction and the displacement is to the right, the cosine of theta cancels out to 1. The net force is 35.31 newtons. Multiply that by 8 meters. And look at that. We get a net force that is exactly the same. Not net force, the net amount of work done. Again, this is how much energy is flowing into our system. There's an increase in the amount of energy flowing into the box. Energy is flowing in because tension is trying to give the box kinetic energy. The tension is trying to pull the box and make it move faster and gain kinetic energy. But friction is also taking some energy out of that box and turning it into internal energy. So friction is really tension is trying to increase the mechanical energy. Friction is trying to decrease it. Overall, because there's more tension than friction, there is a net gain in mechanical energy for the box. Okay, a couple of review questions, then we'll circle back around. During the box's movement, what's the acceleration of the box? Well, we already know the net force now. We know the net force in the y direction is 0 because the acceleration is 0. But in the x direction, we can figure out the acceleration. 35.31 is the net force. The mass of the box, or crate, I keep calling it a box, but it's a crate, is 30 kilograms times ax. We simply divide both sides by 30. And we get an acceleration of 1.177 meters per second squared. That's the acceleration of the box. So we know it's speeding up. And that makes sense because we know that there's an increase in mechanical energy, which means because the mechanical energy is increasing, the only type of energy that can be increasing is kinetic energy. This box is not compressing a spring or moving up into the air. So if the kinetic energy is increasing, it makes sense that the box is accelerating. Now that we know the acceleration, we can figure out how fast the box will be moving at the end of the 8 meters. There's our displacement. We're trying to find VF, and we have A. Let's assume the box started from rest, which it did. We don't have to assume that. We can use one of our kinematics equations. VF squared equals VI squared plus 2AD. No initial velocity. We're looking for VF. We get that the final velocity of the box is 4.34 meters per second. Based on this, we could have found the kinetic energy of the box, or we can find the kinetic energy of the box after it's moved those 8 meters. The kinetic energy equation is 1/2 mv squared. The kinetic energy is what we're looking for. 1/2, 30 kilograms, 4.34 meters per second, whole thing squared. 30 times 4.34 times 4.34 times 1/2, and we get, within a rounding error, pretty much 282.5 joules, which interestingly is exactly the same as the net work done on the box. Now, we should have realized this. The net work was going into increasing the kinetic energy. So we even could have done this backwards. We could have said, here's the net amount of work, which means that's how much kinetic energy has increased. We could have gone backwards and found the speed. And from that, we could have gone backwards and found the acceleration. Okay, so there's actually a bunch of different ways that we could have done this. Now, what if there had been no friction whatsoever on the box? What if we had a situation that looks like this? Everything else is the same except there's no friction. What would happen to the box's speed at the end of the 8 meters? Well, the tension's still the same, so the tension will still be trying to increase the amount of kinetic energy that the box has. But now, you don't have a force of friction, so there is no force doing negative work. There's no force that points back towards the left when the box is moving to the right. No force is doing negative work, so all work goes toward increasing the kinetic energy, meaning the box goes faster. Also, with no force of friction, obviously there's no work done by friction, so there would be no increase in Q, the internal energy. So basically what happens is the box just ends up moving much faster. And this is kind of obvious. You've already dealt with forces. If there's no force of friction, that means there's nothing to cause the box to, there's no force back to the left. There's nothing to decrease this acceleration from what it would be with just tension. The box will accelerate at a greater rate. It'll get up to higher speeds. This is just another way of looking at it in terms of energy. So our conclusion for internal energy. If there is friction present, it reduces an object's kinetic energy. But that energy doesn't just disappear, it is simply transferred into internal energy. It becomes internal energy. Okay, you can't create or destroy energy, so it simply becomes internal energy. I'll wait for the bell. I think that's pretty much it with internal energy. It is kind of a tricky subject in that there's not a defined equation for it. It's really just looking at different situations in which friction is present and understanding where the energy goes and why energy is leaving, why mechanical energy is being turned into internal energy. So it seems like energy is leaving the system, but it's not really. It's just getting transferred into a different type of energy. Your homework has some tricky problems with this, so please make sure to ask questions if you have them. All right, that's it. I'll be back for more videos soon.